Welcome back, everyone. I'm Jason, and today we're gonna chill out with a topic that's both cool and essential to our everyday lives, and that is the topic of refrigerators. Have you ever wondered what makes a refrigerator so cold? How does this amazing appliance keep food fresh and drinks icy? Now, in the old days, there was an ice trade that would actually haul ice from the northern regions of the earth and bring it to the southern regions for refrigeration. So it was a really big deal when refrigerators powered by electricity became a thing. So let's dive deep into the science behind refrigerators and unravel the mystery of their cool magic. And also keep in mind, this applies to refrigerators, but also applies to air conditioners because they run on exactly the same principle. Now, I think what I'd like to do is to first describe the big picture about what's happening. Just listen to my words and I'll try to describe it to you even without any visuals, right? But then I'll put a diagram up and we'll trace through it, and you'll see that once you understand the underlying principle, it's not that magical how they work, but it is pretty cool to learn. Now, to understand how a refrigerator, or an air conditioner for that matter, works, let's start with a simple analogy. I want you to think about the last time you put rubbing alcohol on your skin to clean a cut or a wound. Remember how cool your skin felt. That cooling sensation occurs because the alcohol evaporates very quickly. It has a low boiling point. It turns from a liquid into a vapor, and the phase change at that point requires heat, which it absorbs from your skin, and that is creating the cooling effect. Basically, that cooling effect that you feel is because the body heat is going into the material, which then evaporates. So let's take a few minutes to actually mull this over and sort of feel it in your bones, as I say, because it is the core principle behind how this works anyway, right? For air conditioners and for refrigerators. Basically, when you put alcohol on your skin, it has a boiling point, just like water has a boiling point. And as you know, water behaves the same way. When you get out of a swimming pool, you are shivering because that water is also evaporating. But the boiling point, or the vapor point, of alcohol is lower than water. If you pour the alcohol on the counter, you know that it's going to disappear within a few minutes. Same thing with gasoline and such, but you don't want to really put gasoline on your body, right? So water provides a cooling effect, but because the temperature at which alcohol vaporizes is much lower, then it can vaporize easier with your body heat. So you have your atoms and molecules in your skin, and you have a body temperature, right? Now, the temperature that we talk about every day is really the average thermal motion of all of the atoms and the molecules in your skin. If they're jiggling faster, then you have a higher temperature. If they're jiggling slower, then we say have a lower temperature. Now, what's happening is the alcohol goes on your skin, and the atoms and molecules of your skin are jiggling and bumping into the alcohol, and they're giving energy to the alcohol. But because the alcohol can turn from a liquid to a vapor, as soon as the alcohol molecule gets a little bit of extra energy to vaporize, it detaches from the surface, literally floats away, and it goes off somewhere else into the air. It's still there, it's just in vapor form right there. So because the molecule of alcohol has absorbed energy from your body heat, and because it is sort of detached from the surface and now has flown away somewhere, it has taken that heat physically from your body. Think about heat being the thermal motion of things. Some of that energy from your body has then gone into an alcohol molecule, which has then left the surface of your body. It takes the energy away. That's why you actually feel cold, because the thermal energy of your skin has been transferred to some molecule that's now flying away somewhere else. That is the core principle why alcohol on your skin makes you feel cold. Getting out of a swimming pool makes you feel cold, and that's what we have to talk about and use to make a refrigerator. And this is also, as an aside, why they tell you if you are in a survival situation and you fall into a freezing river with your clothes on, if you climb out of the river and you survive that, you're probably going to get hypothermia and you might die if you keep those clothes on. Why is that? Because it's hard for the water to evaporate when they're trapped in the fiber of the clothing. I mean, it does happen, it's just much slower when you have wool or cotton or whatever trapping the water near your skin. What you really need to do, even though you feel very, very cold initially is to take all of your clothes off, at least temporarily. Hang them up, get them away from your skin so that the water on the surface of your body makes you cold, you're shivering, but eventually that water will evaporate and leave your body and you will eventually feel warmer faster. Now, I'm not a survival expert. I'm not telling you to strip down and just go dancing and you're going to be fine. I mean, you still have to find shelter, you still have to get dry. But I'm saying if you have two people, one person falls into a river, keeps their clothes on, and one person falls into a river with their clothes on and takes them all off, gets dry, gets their clothes dry, puts them back on eventually later once they're a little bit drier, that person's going to have a higher chance of survival. If you wear your wet clothes, you're just not rejecting the heat as well, so you're going to stay cold and you're going to have hypothermic issues. Now back to refrigerators. Modern refrigerators utilize this principle of evaporation and taking heat away through a cycle, something that happens over and over again. And at the heart of this cycle is a substance called the refrigerant, which is constantly changing states between the liquid and the gas phase. The phase change of the refrigerant back and forth over and over again is absolutely central to understanding how a refrigerator stays cool or how an air conditioner blows cold air, because ultimately in an air conditioner you have a fan blowing air over these coils which are cold, and that's how it cools off the air hitting you in the face. So let's do a thought experiment to make it easy to understand, and this is not realistic, but it's a thought experiment, okay? Let's say that you want to make a refrigerator, but you're using water as the coolant because water is everywhere. Now in real life we don't use water for the refrigerant, but let's just say that we have some sort of bucket of ice water right outside of my refrigerator. The ice water is really cold because there's ice in it, okay? And what we do is we pump that ice water inside of the refrigerator, which is nice and warm. It's not cold. Now that ice water is circulating through coils in the walls of the refrigerator. What's going to happen? Well, the water's really cold, so anything warm in there is going to transfer the heat, the vibrations of the molecules in the milk or whatever you have in there, into the liquid traveling through the coils of that refrigerator. What's going to happen? The ice water is going to warm up because it's basically absorbing energy from the contents of the refrigerator. So the ice water, when it gets halfway through the fridge, is not as cold. And by the time it gets all the way through the fridge, it's not cold at all. It's like room temperature water. And then out from the fridge comes room temperature water. So you have ice water going in, and then it cools off the contents, and then room temperature water coming out. Now that's awesome. The only problem is you're going to run out of water because you've put ice in there and you're going to run out of that water. So let's say you're clever and you build a really long pipeline from your refrigerator. I live in Texas, and let's say I pump that water all the way to the North Pole, someplace really cold. And then that water gets cold again because it goes all the way to the Arctic Circle. Then we pump it all the way back down to where I live in Texas, and then we make it go through the refrigerator again. That would work forever. Obviously, the problem is pumping water from that distance all the way to the North Pole, or even a small distance, it's going to consume a lot of electricity. It's going to get, the electricity is going to cost a lot of money. It's just not going to be practical, but it would keep the refrigerator cold. What we need to do is figure out a way that when the coolant comes out of the refrigerator, it's hot because it's absorbed the energy from the inside. We need to somehow make it cold again, right? Without pumping it all the way to the Arctic Circle. And that's what we're going to talk about next, because that's what happens. We circulate the cold coolant, the refrigerant, through the walls of the refrigerator or over the coils in an air conditioner that we blow the air over. But in the process, it warms up the refrigerant. Then we have to somehow make it cool again, and then it goes right back in. That's what we have to talk about next. So here's how it really works. The refrigerator uses a compressor to actually pressurize the refrigerant gas, and that heats it up as it gets compressed. Now, we've all heard of compressors when it comes to refrigerators or air conditioners. It's a central part of the whole thing, right? And so we have to talk about that for a second. If I gloss over it, then you won't understand anything. When you compress a gas or compress anything, it heats up. Why is that? Well, what is temperature? What does it mean to heat up? Well, what that means is the kinetic energy, the motion of the atoms and the molecules in there has gone up somehow. Now, when we compress something, what does it mean? If I have a balloon here and I somehow squeeze it from all sides and I take the balloon this size and I make it this size, I have rammed all of those gas molecules physically together. Now, remember, the gas molecules are moving all the time in all different directions, and they're colliding and bouncing off of each other, and they're bouncing off the walls of the container. Right now, my skin is trillions of air molecules, oxygen, nitrogen, hitting my skin and bouncing off and also colliding with each other. But when I compress compress something, what I'm doing is the walls of the container are physically ramming themselves into the gas. Think about a tennis player hitting a tennis ball. So when I compress the container, it's like a tennis racket just kind of moving on in and colliding with trillions and trillions of gas molecules, right? And bouncing them and forcing them towards the center, and then they start to bounce off and collide with the other gas that's in the center. And so the energy that is coming to increase the temperature of the gas is coming from me physically moving the boundary of the container and making it smaller. So when you compress a gas, it gets hot. I challenge you to go grab a bicycle or even a car and just hook up a bicycle pump to a car tire and pump that tire up with the mechanical motion of you pushing on that bicycle pump. What you're going to find after about 2 or 3 minutes, if you grab the tube there or the hose going into the tire or even the tire itself, you're going to find that it warms up. And it's warming up because I'm ramming over and over and over. The mechanical energy of my arm is going into colliding with that gas, and it's making it hotter. All right, the reason I went through that is because that's fairly easy for most people to understand. But you also have to understand that the opposite process is also true. If gases, when they get compressed, get hotter, then what do you think should happen if a gas or a liquid vaporizes or goes from a small volume to a very large volume very, very fast? In other words, the opposite of compression is expansion. What happens when a gas expands, or if a liquid vaporizes quickly from a liquid to a gas state and gets much bigger in volume? Well, if compressing something makes it hot, then expanding something should make it cooler. And that's exactly what happens. The easiest way to think about it is understanding that ramming the boundary of a container into a gas makes it hotter because I'm giving energy to the gas as the boundary collides with the gas inside. And so as the gas expands, it's pushing against the boundary of whatever it's expanding into, and it's giving up its energy to the environment. Whereas in the compression, the boundary of the container is giving energy to the gas. If the gas is expanding into the atmosphere or into some container, it's giving some of its energy to the movement of the container. And so therefore its energy of the molecules inside must go down. So compressing a gas makes it get hotter. Expansion in generally cools things off. And so that is how a refrigerator or an air conditioner works. We have a compressor that is going to compress the material, the refrigerant, which makes it very hot. But then later on, we're going to expand, flash evaporate the refrigerant, which makes it expand and makes it cold again. And that's what we needed. We needed a way to make the thing cold again so it can go back in and continue to refrigerate the inside of the container. And so the last thing I'll say is if you need proof that this is actually a thing, just like I told you with the bicycle pump, it starts to get hot, go grab yourself a can of hairspray or some other pressurized container of something safe, okay? Some kind of, I'm not talking about the pump where you pump it with your finger. I mean when you hold the button down and then the hairspray comes out. Put your hand on the container of the hairspray, the metal can, as the hairspray begins to fly out. Very soon it's going to get cold. And in fact, if you hold it down for 4, 5, 6 seconds, wasting your hairspray, you're going to find the temperature drops quite a bit. And that is exactly because of what we just discussed. So we have this compressor, and after the compression of the refrigerant, it gets hot, and it's at very high pressure, and it's a gas, and it travels through a series of coils on the back of the refrigerator or outside your house if it's an air conditioner, known as the condenser coils. And as the gas then cools down as it releases heat into the environment, and it turns back into a very high pressure liquid. So at this point, it's a high pressure liquid refrigerant, and it passes through an expansion valve, which expands the volume of the thing and suddenly turns the temperature lower. So it decompresses and it turns back into a gas, and it's colder. The rapid expansion causes the refrigerant to absorb heat from the inside of the refrigerator as it circulates through the cold compartment. So it's cold. That's what we're doing. We made it cold by expanding the material, and then it travels through the refrigerator and it cools the contents within. Now this process takes place in evaporator coils, which are typically located inside the fridge or the freezer compartment. Now this cycle repeats over and over again. As the compressor pulls the gas back in, the whole process starts all over again. So essentially, the refrigerant acts like a heat sponge. It soaks up heat from the inside of the refrigerator and it releases it outside the refrigerator. This continuous cycle is what keeps the inside of the fridge cold and the food fresh. Let me just say here that in science and engineering, there are the laws of thermodynamics, there are the laws of conservation of energy and such, so you never get something for nothing. You might think you're getting this refrigerator to be cold for free, but it's not for free, because really the way to think about refrigeration is the inside is getting cold, but really all you're doing is you're moving the thermal energy from the inside of the box to the outside of the box. And so in order to make the inside cold, you're not really getting something for free. What you're doing is you're making the outside hot. It's exactly the same thing as putting alcohol on your skin. You might feel cold, and so you think you've kind of got something for free here, right? You're nice and comfortable, right? Because you're nice and cool. But actually what you've done is you've moved your body temperature, the energy from your body to the environment through the evaporation process. So it's not like it disappears, it's just moved from one place to the other. And so you're making the outside environment hotter in order to make the inside colder. And if you put your hands behind a refrigerator, again, don't do this unless you know what you're doing, you'll feel that it's warm back there. It's moving the heat from the inside to the outside. And so again, just to wrap it all up, it's a process. If we had our water that was ice cold and we move it through the refrigerator, it's going to cool off the inside, it's going to come out hot. Or warm. And so we take that, we pump it to the Arctic Circle, make it cold again. We get that from the environment, right? For free, quote unquote. And then we bring it back down into the fridge again, and it makes our contents cold again. Sounds awesome. We can't do that in real life. So what we do is the next best thing. We have a refrigerant. What we do is we make it cold by expanding it, by flash evaporating it, and makes it very, very cold. That cold refrigerant goes through the coils inside the refrigerator, and in the process it heats up because it's taking the heat away from everything inside. So as it heats up again, it's useless. It's not cold anymore. So it comes out the back and then it gets compressed and squeezed back down again, because remember, we expanded it. So it compresses it back down. And then it passes through coils, but these coils are on the outside, either outside your house for an air conditioner or outside the refrigerator in the back for a refrigerator. And it goes through these coils to reject the heat that you just picked up from the compression, push it into the environment. And so as it reaches room temperature again, it goes back into the refrigerator and it flash evaporates again, making it cold again. So you don't run out of refrigerant unless you have a leak. And the reason you don't run out is because you're not consuming anything. You're just expanding the refrigerant and then compressing it, expanding it, compressing it, expanding it, compressing it. And so the inside is stayed cold because we just expanded the stuff before it came on the inside. It's nice and cold. And on the outside, we're compressing it and rejecting all the heat that comes from the compression into the outside environment. And that happens in a continuous loop over and over again. Now, I want to talk for a minute about the impact of refrigeration on our daily lives. So before the invention of refrigerators, people relied on methods like salting or smoking or dyeing to preserve food. And the advent of refrigeration totally revolutionized food storage. It allowed things like milk, perishables like meat, cheese, things like that to last much longer. In a refrigerator, milk can last for 2 or 3 weeks, and frozen milk can even last for months. But refrigeration isn't just about keeping food fresh, it's also about slowing down the growth of bacteria, which thrives in warmer temperatures. So by keeping the food cold, refrigerators help prevent illnesses that are foodborne, and they ensure that we can enjoy safe and healthy meals. As I mentioned before, the journey of refrigeration technology is pretty fascinating, to me at least. Early industrial refrigeration units used ammonia for the refrigerant, which is effective but really toxic. So in the 1930s, DuPont Corporation developed chlorofluorocarbons, you've probably heard of these, CFCs, which were thought to be a safer alternative. However, in the 1970s, scientists discovered that CFCs were damaging the ozone layer of the atmosphere, which led to major changes, and we stopped using CFCs. That's a totally different video for a totally different day. Now, since that time, new refrigerants have been developed that are safer for humans, and they're also safer for the environment. These advancements continue to make refrigeration more and more efficient and eco-friendly, ensuring that we can keep our food fresh without worrying and harming the planet. So the next time you open your refrigerator for a midnight snack, I want you to take a moment to appreciate the intricate science at work there. It's pretty incredible, actually, that we have an appliance that uses the principles of physics and chemistry to create convenient and safe and essential part of modern life. I want to thank you for joining me and hanging out with me as I talk to you about this really cool explorations of how refrigerators work. Until next time, I want you to keep exploring the wonders of science. Please do drop me a line. Let me know what you think, and I want you to always remember to stay curious.
Learn anything at mathandscience.com.